Some of the most popular 3D prints are fidget toys, and after printing a ton of them and putting them together with my kids, I noticed that almost all of them with a certain type of movement have one fatal flaw. And that flawed area revolves around, well, things that revolve around. These fidgets are printed on all types of printers with all types of filament, with any level of calibration from none to fully automatic, and anyone at any skill level can assemble them. If you add all that up, the success level goes way down. And I think these fidgets should have a nearly 100% success rate if they can make it off of the build plate. So let me show you the problem and then how easy it is to solve it. And I also tell you why I think it's so important to fix this. So stick around. My kids are starting to get interested in 3D printing and in designing their own 3D prints, and I've been printing some fidgets for them to play with and to try out. Isn't really normally what I would focus on, but they're enjoying them, and I will admit they're a lot more fun to play with than I expected. But when we were assembling some of the most popular fidgets, some were not going together very well. The fit was too tight and parts were breaking. Now I made some tweaks in the slicer and then reprinted the parts, and that's okay, but almost nobody is going to do that. It isn't really precise work. It's also tedious as well. The solution really needs to be made right inside the original model. This model is printed in separate pieces, and I think it's a really good idea because you can print in any color, and for the most part, it is really well done. I don't want to take anything away from the designer. It's tough to design these and have everything work every single time with all of these variables. So I'm using this model as the example only because it is the one that I've had the parts break on me more than once. We have some robust parts. We also have some very small parts, and with the way this is designed, the top locks in using these really neat spring clips. The top, however, does not interlock with any of the other parts to provide support. That is normally something that I would like to see, but I can imagine for ease of assembly it was made in this way. So what we have now is these tiny cylinders that are only supported at the base, and each one is different in size, which is good to make sure that each part can only be put into one place. Some of them are much larger and not really that much of an issue, but these two are very small. So let's print some and then assemble them and see what actually happens. So the first time I put this together with my kids, we couldn't assemble it. So I tried it myself. I decided that drilling out the holes was probably the best idea for that moment. It's not really a great solution. It needs to be printed, then assembled right off of the build plate. The next several times my son tried to do it on his own, the parts just did not go together and the pins ended up breaking. I decided to adjust the model in the slicer by removing some material, and we were able to get something that actually worked. For super strong parts that do not fail, I would have recommended using a steel pin, which fits into a boss on the top and also on the bottom. But again, that's not really great because it's an extra part, it's also extra cost, and we need to wait for delivery. Like anything, the problems are always a little bit deeper than you might think. If the fit is too tight, we're gonna have to push harder, and because the part has infill below it, and if we have hollow areas in there, in some cases, the harder we push, the more likely it's going to be to break just from pushing that piece into place. It's also a little bit hard to make sure to apply the force straight down in line with that axis of the cylinder, so we could break the pin from just that as well. But even if we get it in place and start to move it, there's so much friction, it's probably gonna break off just from rotating it. When we put it together, it was tight and did not want to go at all. There were a few reasons for this. One, the fit's just too tight because of the design. Not enough clearance was added. The print settings might not be quite right. We could have a seam inside there. Well, we will have a seam inside there, and that could be causing a little bit of a bulge. The bottom layer of the mating part may also have a little bit of elephant's foot as well. Now to show the fix, I'm going to be working with the mesh in this case, which I do not recommend at all. It's just a mess to work with and it's super slow in fusion, but I wanted to show the exact part for our solution. So what we need to do first is fill in the areas and beef those problem areas up. And I'm going to be drawing in some circles and trying to center them as close as I can. I'll extrude them to give me some usable shapes to work with. Next, I want to draw in the shape that I want to be my final size, and we're going to need a very small gap. It's good to have a gap size of 0.2 millimeters or 0.3 millimeters, and 0.2 is what the original one had, so I'm just going to use that number again. So I'm going to extrude these cylinders up, but what we're going to do in this case is extrude them with a slight taper, and it only needs to be a very light taper. I'm going to be using 2 degrees for mine. What this taper does for us is gives us a loose fit to start, it gives us automatic alignment, and it will only snug up at the very bottom. It's a good idea to add a chamfer at the base at the transition, and we can also chamfer the bottom of the mating piece as well. But that one's going to be a slightly larger one. We still have the issue of friction if the parts end up being tight, so we can sketch in a very small amount of relief in and revolve that around. It's only an extra 0.1 millimeters, so it will not weaken the pin. For both of these pins, they are now larger at the bottom than the original ones were, and that's the area they'd be most likely to break. But more importantly, we are removing all the issues with the installation, so breakage is also just far less likely. The differences are actually really subtle, but they're important for assembly and also for longevity. But we're actually not done. Those are only the changes in the design. We can also adjust the model in the slicer, and you can do this yourself if you want an even stronger part, or the designer can do this and have it made available for everyone in this way from the start. So you can click on your part and bring in a cylinder modifier. And actually this is great because normally parts are printed with all the same settings, but we can make these parts much stronger by making a few minor adjustments. And one is to change the speed of just these areas. And if we slow down the print in these areas only, we should get a fast print still, but it should be stronger where it needs to be. Now I'm saying that, but I actually don't really know this for sure, so I wanted to run some tests. These are all printed at different speeds, going from the fastest on the left at 200 millimeters per second to the slowest on the right at 5 millimeters per second. Everything else is identical, and they're all printed at the exact same time. So now let's test the breaking point for each. So what's interesting is that they're all pretty close to the same and also pretty strong too, but these just aren't different in speed. They're also different in the way the layers below are extruded. So I've also printed this one, which is printed the way things are normally done. So our first sample, we have the faster speed all the way to the lower speed here, and every single one of these broke at depth. You can see it was not at the surface level, so that's a very good failure point. And this averaged 32.3 newtons for all of these. I have another sample that was just printed all the exact same speed, and you can see here, with the exception of this one, partial break at surface level, but they all have some break at depth. And this one was just deep, so it was applied with the modifier as well. And this one averaged at 28.4 newtons. Again, towards the right-hand side, it seems to be a little bit weaker for some reason. And this is the standard way that you would print. You can see a little tiny bit where it pulled out below, but aside from that, they all broke in the same way. And this is just a normal print. Average a 26.6 newtons for the breaking of this one. So the other method, the one with the modifiers, actually was stronger overall on average. So this test actually showed it's not as much to do with the speed as the interfacing below each layer. This is really easy to adjust to. You can just do it in the model itself before exporting by adding an extra cylinder, making everything into components so that you can import it in as one with the positions intact, and then adjust the extra shape to be a modifier. Now it just needs to be positioned slightly lower than the transition point, and you'll get these extra extrusions rather than this type of extrusion. You can do the exact same thing in the slicer by bringing in the modifier and moving it to where you need it to be. But I did notice during this test that the pins nearest to the auxiliary fan performed a little bit worse, which I did not expect because they were printed slower. So I decided to also run some tests without the auxiliary fan turned on. I also turned part cooling down to 25%, and the results for these tests were again quite a bit better. So again, here is what it looks like, the standard print. These are all the same speed, but speed didn't really come into play a lot for the final strength of each of these pins. And this is what it looks like when we remove some of that cooling, remove almost all of the cooling. And you can see it actually tore out. This one here, rather than tearing out, it broke above. This broke at 39.2 newtons. This broke at 39.2 newtons. Overall, the average was 36.24 newtons, an improvement of 36% above this. So quite a big improvement just by turning the cooling down. And also I had the modifiers in here, so the extrusion was a little bit different below the surface than this one here. So we have better adhesion because of less cooling, and we also have a little bit different extrusion, and that all adds up to a stronger part. And just for reference, this one here, which was the modifier, it is a 7% improvement on average versus the standard method. So not a huge improvement. Less cooling is a much bigger improvement. Now, this isn't something that you can control easily by a modifier, but what I would say is that if you're printing a bed full of parts, you don't need nearly as much cooling. The layers will have enough time to cool before the next layer is applied, and that's going to make for much stronger parts. So here's our final part. You can see the light chamfer on there, larger hole on the bottom, smaller hole on the top. Exact same for this one, just a little bit larger hole, again smaller on the top. And you can see here the smallest of recesses in here, and it's a bit tough to see in there, but the same thing goes. So now all we have to do is put it together. And I haven't modified this at all, so this is just as it is. And that's the fit we get. Beautiful. And with this one, that's the fit that we get. And I would say it is a little bit important for a part like this to have a decent fit, because if it doesn't fit properly, the snaps won't work correctly. So that one snaps really well. A good example of one that doesn't snap as well is this one. It's kind of loose, and it's loose because this is one of the ones that I had to enlarge the hole. So it doesn't snap correctly. And then this piece goes in here. That's got some good snap to it. And then these pieces go inside like that. Perfect. Very happy with how that worked out, and you can see how quick and easy that was to install, and I didn't struggle at all with it. So a very light taper goes a long way to help with assembly. A relief area helps with friction, a chamfered area with reinforcement of the weakest areas, and cooling is oftentimes way too high and affects layer adhesion and should be used only on very small parts or overhangs or bridges. If you're doing the design work, it only takes a couple extra minutes to do all of these steps, but it will save anyone printing these parts a ton of time, save on waste in broken parts as well. Now, if you have any pro tips for getting stronger parts, please share them with everyone in the comments down there below so we can continue to improve. And I wanted to mention as well that I focused on the pins in this video, but the same exact technique applies to any parts that fit together. This piece is too tight and too tough to install for a child. And by adding a slight taper on each of the mating surfaces, it makes the installation that much easier. You could also argue that the smallest pin in this model really isn't needed. The part is kind of captured already, so a slight adjustment to the model could allow the designer to remove it completely. So the reason I wanted to focus on just this one small area in this video is because there are thousands and thousands of fidgets being printed, and if a portion of them, a good portion of them, are being broken during assembly, that's not good. It's just going in the garbage can. It's also depressing for the people that are actually printing these parts as well, expecting to have something go together for them, and instead they get something that falls apart. So although it's a very small area, I think just these slight improvements will make a big difference in the final product. If you're in the market for a 3D printer and you'd like to help support this channel, I have a very short list of my top rated 3D printers down there below in the description. And if this video helped you at all, please hit that like button. It helps the channel to grow and helps to keep me making videos like this. I was picking on this model by Joy Top Toy, but almost all fidget toys have these exact same issues. This one is extremely well designed. There's just that one small area for improvement, and I would make the change and post it as a print profile, but instead I decided to message the designer and leave it to their discretion. Thanks to my patrons for helping to make these videos possible. Take care, and I hope to see you on the next one.